This is a video for OCR Pure Core Mathematics. Complex numbers 6, exponential form. 6.1, the exponential form, z equals r e to the I theta. You may already have studied the Maclaurin series expansions for these functions: sine theta, cos theta, and e to the x. Let's look at sine theta. If you notice, we've got all of the odd powers of theta with alternating signs. And we know that sine theta is an odd function, which means that the sine of minus theta is equal to minus the sine of theta. If we look at cos, starting at 1, cos has even powers of theta, again with alternating signs. And we know that cos is an even function. Cos of minus theta is equal to cos theta. The other thing that we know about these two functions is that for small theta, sine theta is approximately equal to theta. By small theta, I mean something in which theta cubed and above are insignificant. And so for small theta for cos theta is approximately 1 minus theta squared over 2. And you may have seen all of these things relating to sine and cos before. Let's have a look at replacing x by I theta in e to the x. So I'm going to look at e to the I theta. Well, this is just plugging in I theta in place of x in that series expansion. And if I now sort out what happens in these sorts of cases, I theta all squared is going to give me minus theta squared. I theta all cubed is going to give me minus I theta cubed, and of course I've still got my denominators coming through here. When we wrap round to I theta to the 4, it goes back to being positive, and plus I theta to the 5, and so on. Now I can split these up. If I take the odd powers, which are all imaginary, so that's this one, and this one, and this one. If I pull those out as the imaginary parts, I get this lot here. If I pull out the real parts, so that's the 1, theta squared bit, theta to the 4, and so on, I get this here. And if you think back to the previous slide, this is going to be cos theta, and this is going to be I sine theta. So if we have a complex number z, whose modulus and argument we know we can write it as r cos theta plus I sine theta. But from this series expansion up here, I now see that I can write this as r e to the I theta. What about z to the minus 1? Well, that's just going to be this thing to the minus 1. So if we think about that, I'm just going to get r to the minus 1 e to the minus I theta. And that will give me this here. Remembering that sine of minus theta is equal to minus sine theta. And we've used that in there. So in summary then, if we've got a complex number z and we know its modulus and its argument, we can just write it in this form. There's the modulus, there's the argument. So on an Argand diagram, this would be something like this, where that's the modulus and that's the argument. This form, r e to the I theta, is very compact, and it allows us to derive de Moivre's theorem for rational n by using the laws of indices, as you can see here. So if I've got a complex number cos theta plus I sine theta to the n, then that is just e I theta to the n. which is just e to the I n theta, and then turning that back into cos and sine, that's going to be cos n theta plus I sine n theta. And this ability to switch between the two notations we will use in future videos. The next video in this sequence is 6.2, using the exponential form of a complex number.